Okay, so let's start with the sixth section. We have the talk on local certification on graph decomposition and application to minor free classes. And it's a work of Laurent Feuilloley, Nicolas Bousquet, and Théo Pierron. And the talk is given by Laurent Feuilloley.
Thank you very much. Yeah, okay, so the mic is at the right place now. And yeah, well, I will tell you a few things about this paper. So I said it's a joint work with Nicolas Bousquet and Théo Pierron. And well, here is what this paper is about. So there is this field called local certification, and I will start my talk by explaining what it is. And in this field, there is this question of certifying graph minors, which is something else I have to explain what it is. It's something that comes from graph theory and that is relevant here. And well, I will finish with a quick overview of our techniques, probably not a long overview as we have a boat to take. Okay, so, but I would like to start with a kind of scenario. So usually we present local certification as something that comes from self-stabilizing algorithms that can cope with faults. But okay, let's take a slightly different path. So imagine this scenario. So you have the nodes of a network, and they believe that the network is a tree, okay, that is acyclic. Okay, it's supposed to be like this. And it's good because the nodes have a fast algorithm to compute some structure in that kind of network, so a matching, a span, or something. Okay, so nice. But now there is a problem, which is that maybe the network is not a tree. Maybe there has been some faults. Maybe the network is slightly dynamic and it shouldn't be, or something else. And now maybe this fast algorithm that you have for matching, maybe it does not terminate if the network is not a tree. Okay, so that would be very bad. So you start your algorithm and it never terminates because the network is not a tree. So what we would like to have is a way to check that the network is a tree. We would like the nodes to be able to check that the network is a tree. And we would like to do this efficiently because most probably the network is a tree. So you don't want to invest too much memory, too much time, etc. in this checking because most probably it's useless. Okay, so what we would like to have is something such that you can check locally that the network is in the right graph class in general, not just trees, but in a right graph class. Okay, and well, we have a small problem, which is that this is impossible. So you cannot check locally that your network is a tree, and this is kind of easy to get in terms of intuition, which is that, for example, on this drawing, you have this this white node that is, I've drawn its neighborhood at distance 3, but okay, you could go at arbitrary constant distance, and anything this node would see would be something that looks like a tree, okay? And this is true for every node of this network. For every node, if you just take a neighborhood that is not too large, if you do not see this long cycle that is in the graph, then everything looks fine, and you have no reason to think that you are not in a tree. So this is problematic. What we would like to have is to ensure that there is at least one node that can detect that something is wrong, that can raise an alarm, that can say, okay, let's not run this algorithm. This might be problematic. Let's do something else. And well, this is not just for trees. It's very general. Usually you cannot do this local check. But okay, we have like a solution for that. The solution is to say, okay, what if we could put some information on the network to help the node check that the network is indeed in the right class? And well, this is what is called local certification. This idea of having a labeling that helps you to check locally, but it's supposed to be fault tolerant, this labeling. So we require, we have a few requirements on this labeling. So this is going to be slightly technical, but okay, bear with me for 30 seconds. So you have a local algorithm. This is an algorithm that just looks at the node and its neighbors, the label of the node, the label of its neighbors, and outputs a decision. And the decision is either to accept. So accept is something like, okay, I stay silent. From my point of view, everything looks fine. And reject, this is the other decision. This means that, okay, something looks wrong, I raise an alarm, and then, I don't know, you do a reset or something, you stop. Okay, so this is a local verification algorithm, an algorithm that has this kind of behavior. And we want two conditions. We want that if the graph is in the class that we consider, then there exists a labeling such that the algorithm accepts everywhere. So there is a way to convince the node of the network that they live in a network that has the right property. And if a graph is not in the class, then for every labeling, the algorithm rejects in at least one node. So what does that mean? It means that if you have an adversary that chooses the labels for you, so an adversary that is trying to convince the network that the network has the right property, then it's not possible to fool all the nodes. There will always be a node to say, this is supposed to certify that I have a tree, but actually it's not possible. It doesn't match, I reject. Okay, so these are the requirements that we have. And well, this really makes sense. I mean, that's a sensible definition, even though it's a bit complicated. And well, something that is good is that for any graph class, if you forget about computability issue in the term of Turing machines, etc., if you just look at communication, you can always do that. You can always craft such a labeling, but then the labels are going to be very large. And this is sad because you want the certification to be something that uses little time. So this is just local, and little memory also. So small labels. So we are interested in what are the smallest labels possible. Okay. And from the combinatorics side, when you look at, let's say, a graph class and you use certification to study it, then it's also a measure that makes sense because it somehow captures the locality of the class. Okay, so let's be a bit more concrete with the certification of trees. So, okay, if I want to convince the node that they live in a tree, something smart that I can do is to choose a root and then to give to every node its distance to the root. Okay, that's something that I can do. And why is it useful? It's useful because the nodes can check things. So when they just look at the neighbors without the labels, they cannot check anything except that there is no super small cycle. But now that there are distances, the nodes can check things. And here, for example, this node, it has been given distance 4, and it can check, okay, if I have distance 4, then I have exactly one node that has distance 3. This is my parent in the tree, and all the other nodes should have distance 5. These are my children in the tree. Okay, so you can check these distances. So, okay, if I do this kind of checking of the consistency of the distances, well, if I am in the tree, of course, it will accept everywhere because, well, there exists a labeling, which is to put the right distances that allow to make this happen. But now the interesting thing is what happens if I have a cycle? And if I have a cycle, you can prove, and it's kind of easy to see that if I look at the node that has been given the largest distance, so remember that here the labels can be put by an adversary, so it can be very complicated. But if I look at the node that has been given the fake distance, the largest, then this node will always reject. Because this node has at least one neighbor, has both of its neighbors that have distances that are equal or larger, and this cannot happen. Like the distance consistency verification will reject at this point. For example, here, this node has distance 6, and it has a neighbor at distance 6, and this is just not possible, okay, in a tree. Yeah, so this is a kind of well-known example, and in that direction, so the first item is what I said at the beginning. You can certify every class with n square bits. So basically, you would give the adjacency matrix to every node, and then with a bit of details, then you can certify the class. That's the idea. Now we've seen that trees, you can certify them with distances, and this is actually optimal. So log n bits is what you need. So log n is what you need to encode these distances that are between 0 and n. And good news, so also for planar and bounded genus graphs, we have shown recently, and there has been like several techniques to do this, that you can also use just log n bits. So it's not harder than trees in some sense. And well, what we would like to do to understand is like, where does this stop? Okay, what's the power of certification with log n bits. And what these three classes have in common, so sorry, I didn't describe the picture. So you have a tree, you have a planar graph, and you have a graph that is embedded on a bounded genus surface, and this is what we call bounded genus graph. And what these things are in common is that for graph theorists, what they have in common is that they are characterized by forbidden minors. And well, I will spend a few slides to explain what this is. So the informal definition of having a minor is that, well, a large graph G has a small graph H as a minor if H is hidden in G. Okay. So for example, I claim that the small graph on the left, this K5, the clique on 5 vertices, it is hidden in the graph on the right. And what does it mean that is hidden? It means that if I have paths instead of edges and somehow blobs of vertices instead of just one vertex, then I can recover my K5. Okay, so that might be too informal. So the formal definition is that G has H as a minor if one can transform G into H by removing edges, removing vertices, and contracting edges. So what does it mean to contract? It just means that you have two vertices that are linked by an edge. Well, you merge them, and you merge their neighborhoods also. Okay, so this is what a graph minor is. That's something, okay, it might look a bit strange, but in graph theory, it's really like something super, super common. It's really useful and essential. And why is it interesting to us? Well, because these classes that I've mentioned, they are captured by this framework. So a tree is exactly a graph that is triangle minor free graphs, a triangle minor free graph. So if I have a tree, I can never reach a triangle by just removing vertices, contracting edges, etc. But if I have something that is not a tree, then there is a cycle. I can remove everything else, and then I can contract edges on the cycle until I have a triangle. And well, it's well known that planar graphs and graphs of some bounded genus are also characterized by being minor free. So maybe I didn't describe the first line. So we are interested now that we have this notion of minors. We are interested in the graph classes that are the graphs that do not have some minor. So for example, the graph that do not have this K5 hidden in there. Okay, so that's a nice generalization of what we know. So now there is this big question, is it true? Is it true that we can certify in log n bits all minor free graph classes? And well, a weaker version would be like polylog n instead of log n. Okay. And well, before I go a bit into the details, or even in our results, I'd like to highlight why it could be true, why it could be wrong. Okay. So one reason to hope that this is true is that, well, there are graph classes for which we know that this is not true. But these graph classes, they really have a different shape. They really have a different flavor because they are really not hereditary. Hereditary means that, okay, if I have a graph class and I take a graph and I remove a vertex, for example, do I still have a graph that is in my class? Okay, if this holds basically, then it's hereditary. And if it does not hold, then it's non-hereditary. And minors are on the hereditary side, and the graph that we know to have, that require large labels, they are on the other side. So, okay, somehow, at least when you start with this conjecture, it's not immediately wrong. Okay? But now there is a reason to doubt, which is that from the graph theory side, if this were true, then it would somehow mean that we have a constructive way to build all these classes, etc. And maybe that looks too strong for like the graph theory point of view. Okay, so what do we do on this conjecture? So what we do is that we show a special case. And this special case is when the structure that you forbid in your graph, these minors, they are small. And small means either they are less than 4 vertices or slightly more, like 5 or 6, but with some additional information. Some additional assumption on the structure of this thing that you found. So somehow it's good news in the sense that it's a very strong conjecture and we show that it's true, let's say at the beginning. But on the other hand, this is very far from understanding all the minors. Okay. But okay, it's an indication that it's a conjecture that might be true and that it's interesting. Okay, so I have a bit more than 5 minutes left. So what I will do is to give a glimpse of the techniques, okay, that we use. And for that, for concreteness, I will first focus on one class, which is K4 minor free graphs. So what it means is I will focus on these graphs that do not have a click on 4 vertices that is hidden in there. Okay. And well, then you take your book of graph theory from the shelves and you open it, and then there is this theorem that says that a graph is K4 minor free graph if and only if its 2 connected components are series parallel graphs. So that might be good news if you can certify this 2 connected thing and series parallel, and it might be bad news if you cannot do that. And well, the good news is that we can do that. So we follow this natural approach, which is to first certify a decomposition into 2 connected components, and then to certify that each component is series parallel. And here you can see why the title of the paper is referring to decomposition. It's because, like, okay, this minor question is really important, but also the tools that we develop, this decomposition into 2 connected components, etc., they might be useful outside of just this minor question. I mean, which is not minor, but a question about minor. Okay, so here maybe I should define what these things are. So a 2 connected component is a part of a graph such that if I remove a vertex, then I do not split the graph into 2 independent components. So for example, here on my drawing, every blue blob is a 2 connected component, and they are linked by just connecting vertices, and these blobs are organized in a tree. Okay, if there were a cycle of blobs, then it would like not be a vertex that I can remove and disconnect the graph. Okay, and what is a series parallel graph? I will not define in details, but let's say that it is this kind of thing that looks like an electric circuit, where you can take an electric circuit, another one, and then either plug them in series or in parallel. And the key tool we use is something that is called ear decomposition. So that's a funny name, but the tool is really useful. And a plain ear decomposition, or just an ear decomposition, is the following thing, the thing of the picture on the left. So what did I do here? So first you should imagine that the dark blue path, it closes into a cycle. Okay, I just didn't draw the cycle completely, but okay. And now what do? I start with this cycle, this dark blue cycle, and then I add a path, this yellow path, and then another path, this red path, and then the light blue path. You see that I have this iterative procedure to build graphs. Okay, that's okay, a nice procedure. And the thing is that it characterizes 2 connectivity. What does that mean? It means that if I do this construction, then I get a 2 connected graph. And if I have a 2 connected graph, then I can build it this way. Okay, so that's an ear decomposition. It really characterizes 2 connectivity. And well, if you look at nested ear decomposition, where you have, in addition, that each path should be somehow plugged into the same path. So for example, here the light blue is plugged on both sides on the yellow path, and this is called nested ear decomposition, and this characterizes 2 connected series parallel graphs. So like the same tool, ear decomposition, it just it is useful for the 2 parts of this theorem that we use. Okay, so now, okay, just quickly what kind of certification we do. So if I'm the prover that is building the certificates, here's what I will give to the node. So it's a simplified version, but okay. So here's a graph that is K4 minor free graph. There is no K4 hidden in there. Then what I can do is first I compute this decomposition into 2 connected components. Then for every component, I do this nested ear decomposition because I can do that because it's series parallel, and I will describe this to the nodes. I will give, okay, you are in the second ear, you are distance 1 from one of the endpoints, the identifier in which you are plugged are 5 and 8, etc. So I can describe this thing, so you have to trust me that this is something that the nodes can check, and they cannot be fooled if you do it in a different way. So now every blob is characterized, and now I have to prove that, oh, sorry, I forgot to say something. So there is a challenge here, which is that on the connecting vertices, the ones that are shared by two connected components, there might be, this node, it has information for an ear decomposition coming from this component and an ear decomposition coming from this component, etc. So your certificate size might just explode, okay? Because, well, what I've been writing here is log n bits, but then if you have so many of them, then it's not log n anymore. So we have to do some tricks here, but I will not go into the details. And then to certify that you have a tree structure, you just use, again, this distance certification with some additional tricks again. Okay, and well, if I will conclude now. So if you go beyond K4 minus, so for other small minors, you also have such decomposition. Sometimes you have to go to 3 connectivity and well, some tricks, but basically the structure, looking at the decomposition and then certifying the 2 connected component, this is common to all our results. So this is again our results. And in terms of open question, well, the big open question is still the same. We just answered for small minors. Then there are some fresh news, like it was posted on the archive 1 week ago, that basically you can do all planar minors if you use slightly larger certificate, so log square than bit certificate with completely different technique. And if you want to start in this domain, maybe the simplest open problem is, the simplest problem that is still open is the one of certifying K5 minor 3 graphs. And about our tools, well, it would be interesting to better understand how you certify connectivity and what are the lower and upper bounds that you can have on such decomposition. And that's it. Thank you.
Okay, so the next talk is about on explicit space-time trade-offs for proof labeling schemes in graph with small separators. And the authors are Fischer, I hope I am not misspelling too much, Fischer, Rotem, Oshman, and Shamir.
Hello, everyone. My name is Dana Shamir, and I'm going to talk about space-time trade-offs for proof labeling schemes in graphs with small separators. This is a joint work with Fischer and Rotem Oshman. So a little introduction about proof labeling schemes. The idea is that we have a graph and we want to verify some predicate on the graph. We want the nodes to be able to verify the predicate using the help of an external prover that can view the entire graph. But the prover is also untrusted. So the way it works is that each node initially knows its ID, the ID of its neighbors, and it might also have some input. And the prover gives a certificate to each node in the graph. And now each node can view its certificate, the certificate of its direct neighbors, and the input, and decide whether to accept or to reject. And we say the entire proof labeling scheme accepts if all the nodes of the graph accept. This means that it is enough for one node to see there is a problem, and if one node rejects, then all the proof labeling scheme rejects. And we measure the cost of this scheme by the size of the largest certificate. And we require soundness and completeness. Completeness means that there exists a prover that will make all the nodes of the graph accept, of course, in the case the predicate is true. And soundness means that if the predicate is false, then for every prover, the verifier will reject. Okay. So in our work, we investigate an extension of proof labeling schemes called T-proof labeling schemes, or in short, TPLS, which was introduced by Ostrovsky et al. So now, each node in the graph can view not only its direct neighbors, but it can view its entire T neighborhood, meaning all the nodes at distance T from it. So it is pretty much the same as the PLS, only now in the verification procedure, each node can make 3 rounds of communication. In each round, it sends messages to its direct neighbors and receives messages from its direct neighbors. And this way, it learns its entire T neighborhood, including their certificates, and decide whether to accept or to reject. A question that was introduced by Ostrovsky et al. And further investigated by Feuilloley et al. Is whether you can trade time for space. Meaning, if I take a TPLS instead of a 1PLS or the original PLS, can I make the certificate size smaller? So what we try to do, we want to define some compiler or a transformer that its input is some 1PLS, the original PLS, that has certificate size L. And this compiler will transform this 1PLS into a TPLS on the same predicate that has smaller certificate size, L over some function of T. And the prior work in this area of Ostrovsky et al. And Feuilloley et al. Both show the upper and lower bounds for specific problems. This is less relevant to our work because we are trying to find general trade-offs. As I said, we are looking for a transformer that takes 1PLS and transform it into a TPLS. But generic transformations that were done, Ostrovsky et al. Showed that for a universal TPLS, if I use a TPLS instead of a 1PLS, I can save a factor of T. The universal PLS is a PLS where the certificates are the entire graph. So this is a PLS that can actually solve any predicate. And Feuilloley et al. Showed that for any uniform PLS, we can save a factor of T when using TPLS instead of a PLS. And a uniform PLS is a PLS where all the certificates are the same. The prover gives the same certificate to all the nodes. And another thing they showed is you can find the trade-off of for any PLS in specific graphs, trees, cycles, and grids. So for this graph, for any PLS, you can save a factor of T when transforming it into a TPLS. In our results, we show, again, we show a trade-off for a uniform PLS, a factor of at least T. Only now, we use an explicit construction using erasure codes, and Feuilloley et al. Showed it using a probabilistic approach. And we show trade-offs for more classes of graphs, graphs that have small separators. When I say small separator, I mean a small set of nodes or edges in the graph whose removal splits the graph into roughly balanced parts. So notice that in the work of Feuilloley et al. On trees, for example, they used a similar property of trees. And we are going to show it on graph with small edge separators and on graph with an excluded minor, which means they have sublinear vertex separator. Okay, so a general method we use to trade time for space is called partition-based TPLS. And it is a method that we in this method, we generalize the work of Feuilloley et al. So how does it work? First, given a graph, we need to define a partition of the graph into connected components such that each component has diameter less than T. This will allow each node to view its entire component because, as I said before, in a TPLS, each node can view its entire T neighborhood. And we also want some balance between the inner nodes of the component and the outer and the boundary nodes. So the boundary nodes are all the nodes of the graph that are adjacent to a node from a different component. And we want enough nodes in the component, but not too many boundary nodes. And we will see later why. So now, once we have this partition, we can define our transformer, the transformer that receives a 1PLS, the original PLS, and creates a TPLS that has more certificates. So I will define the prover and the verifier of our TPLS. The prover specifies the partition into components, and then it takes the certificates of the original prover, the prover of the one PLS, and it ignores the certificates of the inner nodes. We will see later why it can do it. And for each boundary node, it splits its certificate into smaller pieces. And now it takes these pieces and distributes them among the nodes of the component. Now, the verifier first uses its T round of communication to learn its entire T neighborhood, including the certificates. And now it uses the data it collected to reconstruct the certificates of the boundary nodes of its components. And it compares the certificates of the boundary node with its direct neighbors. And we want to make sure all of its neighbors reconstructed the same boundary nodes. This way, we get that all the nodes in the graph reconstructed the same certificates, of course, for boundary nodes that are common to different nodes. Now, in this moment, we have an assignment of certificates to all the boundary nodes of the component. So the node searches for an extension of this assignment. It searches for an assignment of certificates to the known boundary nodes of the component. And it searches for an assignment that will make the verifier of the original PLS accept on all the nodes of the component. Okay, so it accepts only if it finds an assignment that will make the original verifier accept on all the components. And now, to show this TPLS is sound, we need to show that if the nodes in the graph accept, it means that there exists a certificate assignment for the original PLS, the one PLS, that will make the entire graph accept. And this is true because the boundary nodes, the certificates of the boundary nodes are given in advance, and the certificates of the inner nodes, we can take the certificates each component found, and the certificates that made the nodes of the component accept. And we can stitch this certificate together to a global assignment of certificates to the graph that will make the entire graph accept. And one last thing that we need to explain is how does the prover divide the certificate into pieces, and how does each node reconstruct the certificate from the pieces it has in its T neighborhood. And for this, we use erasure code. So erasure codes allow us to take a message of length L and create some smaller pieces out of it of length L over M. And there are more than M pieces here. So there is some redundancy that allows us to take no more, at least M pieces of these pieces. And from these M pieces, we can reconstruct the original message. So in our case, the message will be the certificate, and the prover uses erasure codes to create smaller pieces out of the certificate, and it distributes these pieces among the nodes of the graph. And now each node that has at least M pieces in its T neighborhood will be able to reconstruct the certificate. And we take M to be some function of T. So this way, we reduce the certificate size by f of T. Now, what's left to define? We need to define a partition that will meet the criteria that I mentioned before. And we need to explain how does the prover distribute the pieces on the nodes of the graph. And this is going to be different for every class of graphs. So I'm going to show an example of one of our works, which is the partition-based TPLS in graphs that have small edge separators. An edge separator is a set of edges that once you remove them from the graph, you get different connected components, such that each component is not too big. And more precisely, the size of each component is no more than 2/3 of the entire graph. And we denote the size of this edge separator by the number of nodes that are adjacent to some edge in the separator. Now, once we have a graph that has an edge separator with small size, we want to define the partition for our partition-based TPLS. So the way it works is that we take an edge separator and split this graph into different connected components. And now for each connected component, we find another edge separator and again divide it to connected components. And we do the same for all the connected components. We stop once we get to connected components that their size is less than t. And now the components of our partition will be the components that are in the leaves of this decomposition tree. And notice that the diameter of this component is truly less than t because their size is less than t. And now we need to explain how to distribute the certificate pieces. So the boundary nodes are all the nodes that are adjacent to some edge separator. And the prover takes the certificate of these boundary nodes and it distributes their pieces among the component that the edge separated. Okay, so notice that also this node is a boundary node and we will distribute its certificate pieces over all of the nodes in this component. And also for this node, we will distribute its certificate over all the nodes in this component. So what is important to explain is why does each node doesn't receive too many certificate pieces? And there are two reasons for this. The first reason is that we said the edge separator has a small size, and therefore not too many nodes are adjacent to every edge separator. And the second reason is that each node receives certificate pieces only from edge separators that are above it in this decomposition tree. And since this decomposition tree is logarithmic, we get that there are not too many edge separators above this node in the graph, in the tree. The tree is logarithmic because each component, every time we divide the graph into different connected components, we get components that are smaller from the original graph. Okay, so this was our build for graphs with small edge separators. And one more thing we show is for a trade-off for graphs with excluded minor. And I'm not going to explain this very deeply, but in general, we use the fact that for any fixed graph, if G excludes this graph as a minor, then G has a balanced vertex separator of size square of n. A vertex separator is very similar to an edge separator, only it's a set of vertices that we can remove them from the graph and get different connected components. This kind of graphs include planar graphs, bounded genus graphs, and more. And we show that you can partition such graphs into connected components such that the ratio between the boundary of the connected components and the number of inner nodes and the number of nodes of the component is no more than 1 over square of t. We build this partition using the R-region decomposition with some changes because as it is, it isn't enough for to meet our criteria. And this way, we get a partition-based TPLS that saves a factor of square t over delta, where delta is the maximal degree of the graph. So what it means is that for any one PLS that works on graphs with excluded minor, we can, if the certificate size of this one PLS is L, we can transform it into a TPLS with certificate size L over squared t times delta. So in conclusion, we showed that for graphs with edge separators with size S, we can take any general 1 PLS and transform it into a TPLS such that the certificate size is smaller in T over S log n. And for graphs with an excluded minor, we can take any PLS and transform it into a TPLS with certificate size smaller by square of t over delta. And this includes planar graphs and bounded genus graphs. And now some questions we can ask is whether there exists a better trade-off for planar graphs, and are there graphs where no trade-off is possible? And that's it. I'm open for questions.
So the last talk of the day, RandSolomon, optimally resilient multi-party random number generation protocol. Okay, no, I don't see. Okay, and it's okay, because it's there. Okay, it's from Luciano Freitas de Souza, Sara Tucci-Piergiovanni, Renaud Sirdey, Oana Stan, Petr Kuznetsov, and Nicolas Quero, and the talk is given by Luciano Freitas de Souza.
This microphone here. Hello, everybody. I'm sure everybody is anxious to vote, but if we need a random number, it will be very handy, our algorithm. So this was an article written by our team on Telecom Paris and together with the COA list. And I like to begin the presentation talking about which kind of systems can deploy RandSolomon. And so we suppose that at most F members are Byzantine, and the system has at least 3 F+1 processes. These processes, they communicate through reliable channels, and they can sign messages and values to prove that it came from them. And the network is partially synchronous. So what we mean by partially synchronous is that there is a period known as global stabilization time, in which the system behaves as an asynchronous system, but later it becomes like a synchronous system. So what is a multi-party random number generator? So first of all, we need to guarantee that the correct processes output the same value, and this is known as agreement. Then the protocol is divided on 3 phases. The generation phase, where processes generate some local randomness and share information. Then a review phase, where they disclose more information, and a final computation phase. The idea is that prior to the review phase, no process can know which number will be decided, nor discard any number from being decided. And then it's a random number generator, and what we mean by randomness is that the values decided by the system follow a uniform distribution. Finally, the system must be alive, so correct processes must eventually decide a value. As you can imagine, this is not a new problem. In fact, it has been extensively studied, and we put a great effort in our related work section in our article. But I like to call your attention to the fact that our solution is partially synchronous. It has deterministic termination, and it provides all properties that I just said. So it's quite new. And we do so with a relatively low complexity, with optimal resilience, and using lightweight abstractions such as deterministic public key cryptography, erasure codes such as RandSolomon, and by organizing the algorithm in a way that processes can retake the steps that should be taken by other processes and check if they are Byzantine or not. So perhaps the best way to see how the protocol works is to give an example. So let's take the simplest system with 1 Byzantine process and 4 processes in total. So the processes, they locally generate a number with n-f blocks. Let's call this an R number. And they encode it using the erasure code. Let's say they use RandSolomon. So now our number, which had n-f blocks, has n blocks. And using any n-f blocks among these, you can retrieve the original R number. Now what the processes do is that they encrypt the element-wise the blocks. So the first block is encrypted on the public key of the first process, the second block on the public key of the second process, and so forth. But our process P4, he is Byzantine, so he doesn't care about it. So what he could do is to generate several numbers and also introduce errors in the values it produces. So what's the difference between an erasure and an error? When we talk about erasure, it's a corruption in a block which we know the position of the block. And an error, it's in a position we do not know. And the Byzantine, what's trying to do here is to split the system, to make processes decide different values, but our system can tolerate it, and it's all right. So these encoded and encrypted values, let's call them S values. The processes, they just send their values to everybody. And notice that the process Byzantine can send different values to different processes, but it's all right. So the participants, they collect n-f S values, and they propose it to consensus. And here, in consensus, we assume a different kind of validity, which is known as external validity. So we require that the decided values must have at least n-f signatures. So in this case, we need values which contain 3 signatures. So for example, the value proposed by the Byzantine P4, like S1, S4 prime, and S4 2 primes, only has 2 signatures. So it won't never be decided by the external validity. All right, so the processes all proposed 3 values, and because of consensus, they will eventually learn the same set of 3 values. Let's say that they learned S1, S2, and S4 prime. So now we begin the review phase. And in the review phase, each process will share the plain value which was assigned to them. So for example, process P1 will share the first block of the numbers S1, S2, and S4 prime. The process P2 will share the second block of the numbers S1, S2, and S4 prime. And here again, our Byzantine is trying to make malicious stuff. He can send, for example, a number which does not correspond to the number it was assigned. But because we use deterministic public key encryption, we can take this number 0, for example, and re-encrypt it into the public key of the number P4 and see that it does not match the number it's supposed to share. So we can reject the value. So after we have collected n-f shares of our S value, we can decode them into the original R values. Now that we have the original R values, we can see if the process who generated a value followed these steps or not. We can re-encode it and re-encrypt it element-wise. And now, at this point, processes would be able, for example, to see that the process P4 had inserted errors on its value. And this is why we can nullify this behavior of the Byzantine. So now we have n-f values, and at least f plus 1 values among them will not be nullified. So we enter the final phase of the computation phase. We take each of these n-f values and we shift them 1 position to the right with increasing steps. Not 1 position, but with increasing steps. So for example, we shift S1 by 0 positions, S2 by 1 position, and S4 prime by 2 positions. And this is a cyclic shift. And now we take the XOR of all the columns, and we have a pre-result. The pre-result will have n-f blocks. And the final step to compute the result will be to combine the blocks pairwise until there is only 3 left in the case of an odd number, and combine the last 3 together. So perhaps you were following me up until the last step. So let's take a bigger example. For example, a system with 3 Byzantine processes and 10 processes in general. And let's see why the last step is necessary. So suppose that before the review phase on the consensus, the numbers that would be decided, unfortunately, 3 of them came from the consensus, from the Byzantine guys. So 3 numbers are totally known by them. Furthermore, these guys, they can read the positions they are in the system. So if the process the processes P1, P2, and P3 are Byzantine, they can read the first 3 blocks because they have the public key. But now, if you see on the right, after we do the increasing steps shifts, we guarantee that in each position, there will be at least one value that the Byzantine cannot know. And although in my example, we only used a single byte for the block for pedagogical reasons, in the true scale system, each block has at least 256 bits. Why? Because we're using the deterministic public key cryptography. So a process, they cannot brute force a value because they would need to test 2 to the power of 256, which is deemed unfeasible. But if you see, for example, on the last column, there is only one value that the Byzantine do not know. And let's say that they really don't want this last column to result in a 0. So what can they do? In this case, if we were to only take the XOR of this column, they would only need to test one value to see if the XOR of the whole column goes to 0. But now, because we combine the 3 last blocks together, the Byzantine cannot discard values anymore. They would have to test, in this case, at least 2 to the power of 512 combinations to discard a value. So the system is safe. So let's just go to a global view of the protocol. Processes begin by generating a random number of n-f blocks. They use erasure correcting code to turn it into a number with n blocks. Any n-f blocks can retrieve the original value. Processes encrypt element-wise the blocks. They share their local random value. Processes collect n-f random values and propose them to consensus. Because of consensus, every process gets the same n-f values, and they begin sharing the plain value of their position. Once you collect n-f plain values, you can, using the erasure correcting code, retrieve the original local random values. Now you can verify that all the steps were done correctly. If anything doesn't sound good, you nullify the number. You take a cyclic shift with increasing steps. You XOR values by column. And in the final step, you combine columns pairwise until you only have 3 left, and you take the last 3 together. So for example, with 10 blocks, you take XOR of B1, B2, it's the first block. The second block is XOR of B3, B4, and the last block is the XOR of B5, B6, B7. So what did we use? We used deterministic public key cryptography, erasure correcting codes, and consensus. As future work, what we've been doing is to integrate this random number generator in blockchains and studying applications of this random number generator into leader election. So I thank you for your attention, and I hope you enjoyed it.